6 engines and 500,000 pounds at Mach 3, the Valkyrie became the fastest strategic bomber that never entered operational service. It reached Mach 3 at 70,000 feet, but a ballistic missile erased the entire strategic bombardment mission before production authorization. Common institutional perception blames program expenditure for cancellation, but a cheaper missile delivered identical nuclear payload without crew exposure. This video explains how the fastest bomber was grounded, not by engineering failure, but by deterrence economics and a corporate publicity photograph. In the late 1950s, the Air Force required a nuclear bomber, capable of sustained Mach 3 cruise above every known Soviet interceptor. The WS-110A program carried one requirement: a nuclear-armed bomber at triple sonic velocity above 70,000 feet. North American Aviation secured the contract, designing a 200-foot delta-wing airframe powered by 6 General Electric turbojets. Maximum departure weight exceeded 500,000 pounds, heavier than a loaded 747, yet engineered for sustained Mach 3 cruise. Wingspan reached 105 feet in delta configuration, with stainless steel honeycomb and titanium selected for supersonic thermal endurance. At Mach 3, the airframe skin exceeds 600 degrees Fahrenheit, forcing reliance on brazed honeycomb construction instead of aluminum. Every surface represented thermal management architecture, designed to survive aerodynamic friction as a primary constraint beyond gravitational loading. The radical proposition was not velocity or material selection, but harnessing the shockwave as a supplementary lift architecture. Folding wingtips dropped 65 degrees at cruise, trapping shockwave pressure beneath the fuselage and generating lift without thrust expenditure. No bomber before or since has employed compression lift, turning hostile aerodynamic pressure into propulsion advantage through shockwave entrapment. 6 turbojets producing 30,000 pounds of thrust combined with compression lift, positioning the Valkyrie as untouchable at cruise altitude. The YJ-93 engines were purpose-built for sustained supersonic cruise, addressing a propulsion challenge no production power plant had resolved. At Mach 3, inlet air exceeds 1,000 degrees, requiring combustion inside airflow already approaching dangerous thermal boundaries. General Electric resolved the thermal constraint through JP6 kerosene, because standard fuel would decompose inside the superheated intake architecture. 6 engines received airflow through a rectangular inlet system, representing the most complex aerodynamic challenge across the entire program. Intake air requires deceleration to subsonic velocity in inches, where any disruption triggers compressor surge or catastrophic unstart. Movable inlet ramps operated through analog computation, adjusting hundreds of times per second to maintain airflow across 6 engines. The propulsion system functioned as integrated air management, where inlet geometry and bypass regulation operated as unified subsystems. Delta wing depth reached 70 feet at root chord, housing fuel reserves and landing gear inside one massive aerodynamic load-bearing structure. Hydraulically actuated wingtips remained flat during subsonic flight, then dropped at supersonic velocity to trap shockwaves and increase stability. No prior aircraft operated movable wingtips at Mach 3, requiring actuators to function under 600-degree loads and aerodynamic pressure. The cockpit enclosed pilot and co-pilot inside an encapsulated escape system, because conventional ejection offered zero survivability at Mach 3. The escape capsule sealed around crew and ejected as pressurized unit, carrying oxygen and survival equipment in spacecraft configuration. North American constructed 2 prototypes designated AV-1 and AV-2, with the inaugural flight departing Palmdale in September 1964. By October 65, the aircraft achieved sustained Mach 3 cruise, validating compression lift and propulsion architecture through performance data. The Valkyrie performed to specification across every parameter, but the strategic environment it was designed for had already dissolved. If you want to understand the engineering behind systems shaping modern warfare, subscribe and follow one platform analyzed per video. The WS-110A program ranked among the most expensive defense efforts, consuming national priority funding across the 1950s. Total program expenditure exceeded $1.5 billion in 60s currency, translating beyond $12 billion in contemporary valuation. Each airframe demanded stainless steel honeycomb through manufacturing techniques that North American invented during the development cycle. Honeycomb brazing occurred inside industrial ovens under precise thermal regulation, where a single defect compromised structural integrity at cruise. GE manufactured fewer than 20 YJ-93 units, each hand-assembled with tolerances unsuitable for mass production replication. After every high-velocity sortie, The aircraft required thermal inspection, checking each joint and panel for heat cycle fatigue across weeks. Operational burden of Mach 3 extended beyond fuel expenditure, encompassing total maintenance cost at the boundary of material science. But the real narrative concerns timing, not expenditure, because a missile installation in Montana was restructuring the strategic landscape. In '57, the Soviet Union launched Sputnik. Within 3 years, both superpowers possessed ballistic missiles, altering deterrence architecture. A ballistic missile delivered nuclear payload to coordinates in 30 minutes, requiring no crew at a fraction of bomber cost. The institutional arithmetic was severe. A $700 million bomber taking hours while missiles struck within minutes from hardened silos. Secretary McNamara recognized the disparity in '61, reducing the B-70 from production fleet to a research-only prototype program. The U-2 shootdown over Soviet territory confirmed vulnerability, proving that 70,000-foot altitude offered no survivability guarantee. The Valkyrie was not terminated by performance deficiency but by relevance, as deterrence migrated from crude bombers to ballistic missiles. Following cancellation, both prototypes continued research flights, collecting supersonic aerodynamic and propulsion data from Edwards Air Force Base. NASA joined the program using the Valkyrie as atmospheric laboratory, generating data feeding supersonic transport and future platform development. The Valkyrie's consequential moment was not a research sortie, but a publicity formation organized by GE for corporate photography. On June 8, 66 GE arranged 5 aircraft in formation, all GE powered with the Mach 3-capable V-2 as centerpiece. Flying alongside were an F-104 Starfighter and F-5 Freedom Fighter, accompanied by a T-38 Talon and F-4 Phantom. Joe Walker piloted the F-104 as NASA's decorated test pilot, holding X-15 altitude records across thousands of flight hours. The Delta Wing generated powerful wingtip vortices at cruise, creating invisible rotating air columns sufficient to destabilize adjacent fighters. Walker's F-104 drifted into the right wingtip vortex, rolled inverted on contact, and struck the stabilizer, causing immediate disintegration. The Starfighter fragmented on impact, killing Joe Walker, ending one of the most accomplished experimental aviation careers at 45. The Valkyrie sustained 16 seconds of flight with both stabilizers severed, before entering an unrecoverable flat spin trailing debris. Co-pilot Carl Cross perished when the ejection capsule failed during spin, while pilot Al White escaped through partial capsule activation. A V-2 was destroyed on desert impact, eliminating the sole Mach 3 validated prototype that confirmed compression lift in operational flight. $12 billion in valuation alongside 2 fatalities and 1 prototype lost through a corporate photograph rather than engineering failure. A V-1 continued NASA research until February '69, completing 83 flights before retirement as the surviving prototype. The surviving airframe resides at National Museum in Dayton, 200 feet of stainless steel and titanium grounded by history. The Valkyrie never entered service or delivered combat ordnance, but its engineering contributions dispersed across every subsequent supersonic development. Inlet architecture and thermal management transferred into the B-1 Lancer, which inherited the original supersonic penetration bombardment mission. The B-1 flew at Mach 1.2 through low-altitude terrain following penetration, carrying cruise missiles instead of gravity ordnance. Escape capsule technology migrated to the F-111 crew module, establishing design lineage from the Valkyrie ejection architecture. NASA research advanced understanding of sonic boom propagation, atmospheric dynamics, and structural limits of sustained supersonic cruise. Aerodynamic data informed Concorde design boundaries, because the Valkyrie's thermal challenges anticipated commercial supersonic constraints. The SR-71 addressed identical Mach 3 thermal challenges, selecting titanium over stainless steel and reconnaissance over bombardment. Both platforms proved sustained Mach 3 flight through different philosophies, but only the Blackbird found a mission justifying institutional cost. The XB-70 retains classification as heaviest and fastest bomber ever flown, a record unchallenged across more than 60 years. No nation has attempted replication because the strategic requirement dissolved, as missiles and stealth replaced velocity as deterrence currency. The Valkyrie represents timing rather than deficiency, a platform arriving after doctrine governing strategic bombardment had shifted. It demonstrates that engineering brilliance provides no guarantee of relevance when a simpler missile eliminates the rationale for deployment. The Valkyrie surfed its shockwave at Mach 3 and proved compression lift, then sat in a hangar while warfare evolved. It flew 200 feet long and 6 engines wide, a material endurance threshold no subsequent military aircraft has approached. Doctrinal shift from crude bombers toward unmanned precision continues accelerating, and the platform inheriting that evolution is the B-21 Raider.